Hello everyone, this is Charishma from Triple Department. Welcome back to the video lecture on database management system, that is unit number 5, database design. So this unit is all about dealing with the different topics related to a good database design and what are the concepts that we need to take care while designing a database. That means at the schema level. So whatever you're studying here in this unit number 5 is all that you take care at the schema level. So you know what's meant by a schema and what happens once the schema is designed. Once a schema is designed by the data admin, the programmers start working on the database is your next level. That is your logical level. So one thing is very clear over here. Whatever you're going to study in this unit regarding the database design is about the physical level. That is at the schema level. So in this unit, you will be covering the topics like what are the different concepts or different elements that need to be satisfied to say whether a particular database is a good database or bad database. So what is meant by a good database and what is a application or what is the use of having a good database? And next one, you'll be looking into the concept of redundancy and anomalies. So why we should not have redundant data in the database and how to overcome if you are facing any redundancy aspect in your database. So that is one more topic. And next we'll be looking into the functional dependency aspect. So what is meant by a functional dependency and how to link up what is the use of this functional dependency in determining whether a database has been designed properly or not. And then we'll be looking into different types of functional dependencies and what are the rules that we have to ensure whether a functional dependency is satisfied or not. Like you will be having around 4 to 5 rules to be studied over here to which help you in determining the functional dependencies between the attribute. That is one concept, and one more concept is about the decomposition. So what is the role of decomposition in maintaining a good database? How to decompose a particular database or a table into smaller elements or smaller tables, and what is the use of the decomposition. And next we'll be looking into the aspect of dependency preservation. So like how you have functional dependency, if you are going with the process of decomposition, how to preserve that functional dependencies of the attributes. And next one, last and important topic, that is normalization. So let's look into each and every topic in detail. What does each of it, the topic, and what is its role in a database design? So our first topic is about a good database design. So I can say there are mainly two principles that need to be satisfied to say if that particular database is a good one or not. My first principle is there should not be any duplicate information. There should not be any duplicate information. So whatever the data that is stored in a particular database, it should not have a duplication of data or repetition of data. So what happens if the data is repeated? The same data is being copy pasted here and there, and whenever you want to retrieve the data from a particular table or or a set of tables, there might be a chances of inconsistencies that may occur over there. And also there might be chances of having some null values, and there won't be any guarantee like whatever output you have received from that particular table which is carrying duplicate data will be right or wrong. There's no guarantee like it will be right. So there's a chances of errors. At the same time, this also leads to inconsistency. So I said in my unit number 1 that a good database or whatever the database you are designing, you make sure that there won't be any duplication of information. So there should be a unique data to be maintained or unique records to be maintained in any database. So that is my first principle that has to be satisfied. Next one, the next principle is, that is the second principle, is about the correctness and completeness of information. So you make sure that the records that are maintained in any database are correct. No incorrect information should be encouraged in a database. At the same time, the completion of information, when you start filling the data of a particular record, you make sure that you're not leaving any null values in any of the attributes. So you have to fill one or the other data in those attributes and make sure you're not leaving any blank spaces over there. So what happens if you leave null values over there? So when you are trying to pull out the data using your queries, this may lead to some incorrect information to be pulled out as your output. So in simple, my first principle is no duplicate information, and second principle is correctness and completeness of information is again very important. Let's proceed for the next slide. So here are the few aspects that are just uh, made in a short form about a good database design. So first one is, divides your information into subject based tables to reduce the redundant data. So what is a solution I have to overcome the redundancy? That is, if you are having a huge amount of information to be handled in a database, you make sure that you categorize the information in the form of categories. Just divide the complete data in the form of categories, and then maintain a separate table for each type of category so that the redundancy won't happen. The same data will not be copy pasted here and there. So one category carries only certain amount of data and the other category carries its own relevant data. So next point is about providing access with information. It requires to join the information of two tables together as needed. So you, in order to, it happens like if you want the data from one table and also from the other table, like you're trying to retrieve the data from two different tables, in that case there should be provisions provided to make sure that both the tables are joined together. Next one is about ensuring accuracy and integrity. So whatever the data you are trying to, or you're demanding from your database with the query, there should be the accurate information pulled and displayed in front of you. The database design should happen in such a way that the information what you demand for should appear in front of you in no time. So accurate it should be. And next one, it should accommodate the data processing reporting needs. So there should not be any clumsiness in retrieving the data. So if you are expecting a certain data to be in front of you, the processing thing should be in a proper and well established manner. So these are the points that are to be satisfied to say that a database design has happened in an effective and in a good manner. Let's move further. That's what we have studied. So all these points has been separated in a separate topic, that is determine the purpose of the database. So you need to be very clear, like these are very similar to the 6-step design process what we have studied in unit number 4. So here you need to first analyze what is your purpose of the database, why you are proceeding with this particular database design. It should be your first step. That has to, the purpose has to be properly understood by you. Next one is find and organize the information required. So you just pull out all the information that a particular database has to handle and organize them according to the categories, like how I just spoke now. Next one is divide the information into the tables. So when you have bulk amount of information collected by you, just divide them in the form of tables and turn the information items into columns. So again, the table should be have provided with the appropriate attributes in that. All the appropriate attributes should segregate the table information into each category, subcategories. Next one is specifying the primary key, which is very, very, very important. No primary key, that means there's no meaning for the table that has been designed by you. So there should be at least one element or one attribute of a table that is making your data unique. So that is very important. That's why it's very, very, very important for you to specify a primary key for a table. Let's move on to the main topics of this particular unit, that is the database design. The first and important topic is about the redundancy and anomalies. So redundancy, let me tell you what is meant by redundancy first. So like just now we spoke, a duplication of data. That means it is a condition where you are trying to create the database with the same piece of data at different locations. So if I'm having two tables and I'm maintaining a record of a particular student whose roll number is 2, and the record of this particular roll number 2 is again found in one more table, what does it mean? I'm trying to maintain the same record in more than one table, which is nothing but redundancy. I'm maintaining the record in two different places. So this condition is called as redundancy, something like duplication, what I've spoke now. So this redundancy will lead to several problems in your relational schema. It leads to several problems in relational schema. Let's see what are the problems that we are going to face here. The first one is redundant storage. Obviously, when your data is duplicated again and again, this means that it is occupying enough memory here and there. Instead of maintaining one record and certain memory in one table, what is that we are doing? The data is being duplicated here and there, and obviously wherever the data has been duplicated, the memory will be occupied over there. This leads to problem in memory efficiency. This leads to problem in memory efficiency. Next one is updation anomalies. Let's take an example and try to understand these anomalies, that is updation anomalies, insertion anomalies, and deletion anomalies. So let me go to the example directly. Yes. So this updation anomalies, if this what happens if you are trying to update any of the values over there. For example, I'm trying to update one of the values of record number 2. So I have a student whose roll number is 2 and I want to change one of those values, that is address, in one table, table number X, and this updation will automatically reflect in table number Y, which is carrying the same record. So, which is not a good idea. So, this leads to an inconsistency in the data retrieval process. So, all the other copies, like how you can see, if one copy of such data, such repeated data is updated, then inconsistency is created unless all other copies are similarly updated. So similar updation problems will happen over there. Next one is insertion anomalies. So what happens in insertion anomalies? Due to this insertion process, new record repeated information gets added to the relational schema. So the insertion what you do in your new record will automatically gets updated in your main schema. That means it is going to affect your main schema itself, which is not a good idea. And next one is deletion anomalies. So if your data or deletion of a particular record happens, some other information record related to that particular thing also gets deleted. You know, a database is something where different tables are linked up. No table is acting like an independent element. Each of the attribute of a single table, and also the tables are interlinked among themselves. So if you assume There are duplication of records or duplicate records found in two different tables. And what did I do? This table carries its own relationships among the attributes. And if I delete any one of those records in table number 1, then obviously it is going to delete all the relations that it has with table number 2. So this should not happen, right? So the deletion of the record should not affect the relations that is being maintained for the other table. So this is one more aspect that need to be taken care in the redundancy condition. The first one is about the memory storage, next one is updation issues, insertion issues, and then the deletion issues. Now, once I think the concept of redundancy is clear right now. Now let's go to the functional dependency concept. So what is meant by functional dependency and what is the role of the functional dependency in the designing aspect? So let me tell you this particular functional dependency aspect in a simple language. So it is nothing but creating a relationship between the attributes. So simple it is. What is that we are going to do here? You are going to create relationship among the attributes. For example, you assume there's one table called as a, and this table has its attributes 1. I'm just mentioning the attribute names as 1, 2 and 3. 1, 2 and 3. So it happens like each of these attributes are dependent among each other. So if there are any dependency conditions existing between the attributes 1, 2 and 3, that is called as functional dependencies. So this functional dependencies has its own role in the database design. Let's see what is the role of the functional dependency. Okay. So before that, how to represent the functional dependency is my question. So you represent your functional dependency like x tends to y. So you can replace this x with any element, like you can also see like a tends to b. The important thing is the what is meant by a right part and what is meant by the left part is a question. So you can represent any way. But you need to know what is meant by right hand representation and what is meant by left hand representation along with the arrow symbol. So what is meant by left hand side part of functional dependency? It is called as determinant. Left hand side is called as determinant, and the right hand part of functional dependency is called as dependent. That means here x is an attribute which is going to determine y. X is an attribute which is going to determine y. That means the y is something that has been obtained by x. So x is a king kind of element, and it is going to create another or make the other attribute to depend on itself. So the one which is determining the other attribute is called as determinant, and y is a dependent. So this y is its existence of y is dependent on the x. That's why it is called as dependent attribute. So this is the basic representation of a functional dependency. Now let's see what is a left hand side element and right hand side element. So we know we just gave a name for right hand side and left hand side element. Now we'll try to understand what type of attribute should be written on left hand side and what type of attribute should be written on right hand side. So right now something would have struck your mind. What should be the attribute that is determining the other attribute? Then definitely it should be a key, isn't it? So a primary key is something that has to be written on left hand side, and non-prime non-key attribute should be written on the right hand side. So let me explain this one with an example. So you assume you have a table with attributes called as employee ID, employee name and employee address. So you just mark the primary key of this particular attribute, that is employee ID. So where is this employee ID supposed to be written? Employee ID should be written on the left hand side, because the employee ID is a key which is going to help in determining the other attribute, that is employee name. So just write left hand side element as employee ID, put an arrow mark, and then write the non-key attribute, that is employee name. Or you can also replace this employee name with employee address. Even that satisfies the functional dependency concept. But you make sure that the left hand side component should always be a key or a primary key. Let's move further. I'm going to divide this concept of functional dependency into two concepts, that is trivial and non-trivial conditions. So when can I say a particular functional dependency as trivial and non-trivial? So first one is trivial functional dependency. So trivial functional dependency is something when our right hand side attribute is a subset of A. Right hand side attribute is a subset of A. That means I'm trying to form a set of key attributes on my left hand side, or I can say I'm trying to form a super key set along with the primary key. So let's go to the example and try to understand it in a better way. Consider a table with two columns. How many columns I have? Two columns, that is employee ID and employee name. Now you look here, I'm trying to form a super key over here, employee ID with employee name. This combination is forming a super key. And this employee ID, you look here, when I say this employee ID comma employee name is determining the attribute called as employee ID. This is said to be a trivial functional dependency. How? Because this employee ID is a part of subset. You see, employee ID is also present in the subset of employee ID and employee name. That means this employee ID is a part of the subset. That's why I say this one as a trivial functional dependency. So apart from this, there's one more condition through which we can say a functional dependencies are trivial, that is self-dependency. So A tends to A or B tends to B. This condition is also taken as trivial functional dependency. Now look into the example directly. Employee ID determining the employee ID itself. Employee name is determining the employee name itself. So it's a very common sense element, right? So that means an attribute is trying to determine itself. If I'm a person, I'll be determining myself first, right? Then only I'll be going for the other attributes to determine. So I'm determining myself is the first priority what I give. Then obviously the attributes are also determining themselves. That means they also come under the category of trivial functional dependency. So in short, what is meant by trivial functional dependency? Trivial functional dependencies functional dependency is said to be trivial in that means the B should be a subset of A. B should be a subset of A. That means B should be a part of A elements. Next one, let's see non-trivial. So if you have understood the concept of trivial functional dependency, then non-trivial functional dependency is quite opposite to that one. What is that? If I have A tends to B, in that case, this particular B is not a subset of A. B is not a subset of A. If it's a subset of A, then it is called as trivial. If it is not a subset of A, then that is said to be a non-trivial functional dependency. So if you try to find an intersection between A and B, that means if you are trying to form an intersection between A attributes, A subset of attributes and B subset or B set of attributes, in that case what should be the value? It should be null because there are no common elements present here. and B is not a part of A. Obviously, when B is not a part of A, then no element is common between A and B. In that case, my value should be null, isn't it? So this is called as complete non-trivial condition. Example is an ID determining the name. So you see, name is not part of ID. Both are acting independently, and in case this ID is something which is going to determine the name, this comes under non-trivial condition. Next one, a name determining the date of birth is again a non-trivial condition because I don't have any set found on my left hand side, and date of birth is not a part of that set. In that case, this is also non-trivial functional dependency condition. So now let's look into the set of rules of that that helps in the functional dependency concept. So the set of rules what I'm studying or trying to explain now are called as Armstrong's axioms. Armstrong's axioms. You can also call them as basic inference rules. Basic inference rules. So what is the need of these rules? So these rules are used to conclude the functional dependencies on a relational database. So these rules are something which will help you or guide you in forming the functional dependencies for a particular relation or a particular table. If you have around n number of attributes, so you can't visually analyze which attribute is dependent on the other one. So you have certain rules that will guide you and help you in finally framing on which attribute on which set of attributes one particular attribute is depending on. For example, so I assume our table has attribute A, B, C and D. So here around you have 5 attributes and you can't visually analyze which one is dependent on which. In that case, you will be forming a closure set called as A plus, and this closure set will tell me or it will frame a set of attributes in a group. So this group will be written in the flower brackets. If I write something like this, it means that the A is an attribute that is having relation with B, and A is also having relation with C, and A is also having relation with D, and it is also having relation with any of these combinations. So this is how this is how you will be creating closure set for a set of functional dependencies in a table. And how to form the closure set? So here are a set of rules that you have in front of you, which help you in guiding those functional dependency closure sets. So in this 6 types of rules, your first rule is reflexive rule. So what is meant by reflexive rule? So in a reflexive rule, if y is subset of x, if y is subset of x, then x determines y. So obviously this was studied just now. So when you have the right hand side component of a functional dependency, a part of x. So for example, assume they have y over here and my left hand side components are x, y and z. So check whether this y is a part of my left hand side component. Yes. So y is a part of the left hand side component. It means it is following a functional dependencies x tends to y. So I'm naming this set as A and also set as B. So as this y is a part of this closure, then obviously the functional dependency is satisfied over here. This is the reflexive rule and I call this one as inference rule 1. So next one is augmentation rule. So augmentation rule is otherwise called as inference rule 2. So this is otherwise called as partial dependency. Let's say why is this called partial dependency? So assume I have attribute x and also attribute y, and this x is determining y. This x is determining y. So when I put a common attribute on both the sides, if I determine or if I put a common attribute on both the sides, that is left hand side and right hand side, in this case, again the functional dependency is satisfied over here. The functional dependency is satisfied over here. That means if x determines y, then xz determines yz for any value of z. That means you're putting a common attribute on both the sides, then the rule will not be violated, still the functional dependency will be carried forwarded. And this is called as augmentation rule, otherwise it is called as partial dependency. Next one is the transitive rule. So what is this transitive rule? Say if x determines y and y determines z, then x must also determine z. So this is very similar to similar to something what you write a is equal to b and b is equal to c, and obviously a is also equal to c is the condition, isn't it? The same way, if x is determining y and this y is determining z, then obviously x should also determine z. So this is the transitive functional or transitive rule or inference rule number 3. Next one is the union rule. So what is this union rule going to say? If x determines y and x determines z, so that means the same x is determining y and the same x is determining z also. In that case, x must determine y and z. So you're writing that functional dependency finally something like this: x tends to yz, that is a product of y and z. So I should not say product, but it's a combination of y and z. X is also determining the combination of y and z. So this is rule number 4. Let's proceed further for rule number 5, that is decomposition rule, that inference rule number 5. So it is otherwise called as project rule. The other name of decomposition rule is called as project rule. So this is something reverse or opposite to that of union rule. Let's see how it happens. So here you have the direct condition given, that is x is determining the combination of y and z. If x is determining the combination of y and z, in that case you can split this particular combination into two different functional dependencies and write something like this: x tends to y and x tends to z. So this is rule number 5. Next one, let's go for rule number 6. So if you want, you can also look into the proof given over here. So next one is pseudo-transitive functional dependency. So what is this pseudo-transitive functional dependency? It says if x determines y, that means you remember whatever the x, y and z I am mentioning here, these are nothing but the attributes of a table. These are nothing but the attributes or the column names. So you're trying to pull the relationship between the attributes using the functional dependencies. So let's move back. If x determines y and yz determines w, then what happens? If x determines y and yz determines w, in that case xz determines w directly. Xz determines w directly. So this is the pseudo transitive rule what you have. Let's move further. So next aspect of this particular unit is the decomposition concept. Again, very important aspect. So name itself says decomposition. That means what are you trying to do over here? So you are trying to break your huge table into multiple tables. Can you even guess what is the need of breaking a huge table into multiple tables? Simple. It is nothing but categorizing. You are trying to segregate your huge data in the form of categories. You're forming a sub attributes of your main relational schema so that the data design happens in an effective manner. And if the data design happens in an effective manner, obviously the retrieval and operation on the data base will also be lead to a convenient result. So you consider a table over here. Let me explain this with this example. Employee department. Look into this one. Employee department. So how many attributes I am carrying over here? This is employee ID, employee name, age, city, salary, department ID, and department name. So among this, so what is that I'm doing here? I'm clubbing out the data of the employee along with the department details, that is department details and the employee data. So what is happening here? This is encouraging the repetition of data here and there, repetition of data, which is not a good idea. So in that case, what you have to do is you can split the above table in the form of two relational schemas. The first one is a separate employee schema with the attributes employee ID, name, age, city, and salary, and department table in a separate form, that is department ID, employee ID, and department name. So if you want to retrieve the data from both the tables, you just join both the tables and you can retrieve the data according to the conditions given in a query. So what are the problems that we face if we don't go for decomposition? The first problem is, given instances of a decomposed relation, we may not be able to reconstruct the corresponding instances of original relation. For example, you assume your main table A has been splitted into B and C. So has been splitted into B and C. So that means splitted in the sense you decompose table A into two tables, that is B and C. And now when you join these two tables back, so there may not be a scenario where you get your original table A. What should happen exactly? If I join the splitted tables, then obviously I should be getting my original table back, isn't it? But there's a chance of missing out certain attributes which may not lead to my original table. This is one main problem what you face in the decomposition process. There's one more problem what you have to face is, each table carries out its own functional dependencies, isn't it? So if I speak about table A would be having certain set of functional dependencies. So this attribute is dependent on this one and this attribute is dependent on this combination of attributes. So in that case, these functional dependencies of A, when it is decomposed to B and C and again joined back, so the original functional dependencies, my previous functional dependencies may not be attained. So there might be some losses in the functional dependency. Few functional dependencies might have been vanished or they might have gone somewhere. So in that case, these two issues are what you're going to face in the decomposition process. Let me repeat. Your first problem is, when you again join the decomposed tables, you may not get your original table because some attributes might be missing over there. And the second one, again, if you join both the tables, some of the functional dependencies of the main tables would have vanished. So these are the two problems that you need to overcome while undertaking the decomposition process. So look into the last sentence. Decomposition is used to eliminate some of the problems of bad design like anomalies, inconsistencies, and redundancy. So here your mind has gone into two ways. So first one, you know the decomposition is having certain advantages, like it is going to overcome anomalies, it is going to overcome inconsistency condition along with the redundancy. On other hand, if you go for decomposition, we just discussed that there might be loss in certain functional dependencies and also there might be a loss in certain attributes if they rejoin together. So which one should we look into the problems or should we go with decomposition because as they are having advantages? So see, the advantages of decomposition are higher compared to the problems. Any method has its own advantages and disadvantages. You need to compare both of them, and if you feel like advantages are more compared to the disadvantage, then you have to proceed with the method. And second, you have to take care of the disadvantage conditions. So here we have two disadvantages what you have found in decomposition process. Now let's see how to overcome those decomposition problems and proceed with the decomposition technique in the database. The first one just now, like what we have discussed, that is lossless decomposition and dependency. So if you want to say that the decomposition that has been handled in a database is right, is going effective, in that case you have to prove that the decomposition is lossless. Lossless means there should not be any missing attributes if they are joined together again. At the same time, there should not be any loss in functional dependencies. There should not be any loss in the functional dependencies. Even the functional dependencies should be preserved, and also there should not be any loss in the data. So if you promise these two conditions, then we say that the function decomposition process has been succeeded. So you have to look into the lossless decomposition concept and dependency preservation concept in the concept of decomposition. Very, very, very important concept again. So let's move further. When can we say a particular decomposition is a lossless one? Now you assume you have a table A that has been decomposed into B and C, and now you have to use certain rules, or you have to check whether this particular decomposition has created any loss in it or not. So how to see that? So these are the conditions what you have in front of you. The first one, applying a union operator. Second one, you go for intersection operator. And last one, you have to check for the common attribute present between these two relations. So now let's proceed. The first checking condition, what is that? Union of relation R1 and R2. So here I have mentioned them as B and C. So let me name it. So A has been decomposed into R1 and R2. You assume the A has been decomposed into R1 and R2. So I am renaming this one R. A is also renamed as R. So when R is decomposed into R1 and R2, and if you apply union operator between the attributes of R1 and also the attributes of R2, so what is this union operator going to do? It is going to act like an OR condition, or condition. That means it is going to pull out the attributes present in table 1, or either in table 1 or table 2. So when you apply union operator between attribute R1 and R2, then I should be able to get all the attributes present in the original table, that is R. So no attribute should be missing over there. In that case, I say the decomposition is lossless. Next one is intersection operator. So here, if I apply an intersection operator between attributes of R1, that attributes of R1 and attributes of R2, you think of yourself what should be the output. So when I speak about R1 and R2, if I put an intersection, that means it is acting like an AND operator. So it should give me the output of those attributes which are present in R1 and also R2. So can there be any common attribute? So it should be under not null condition, because among this R1 and R2, you have one attribute in common. What is that attribute? That is a key attribute. So this key attribute is acting like a primary key in the relation R1 and foreign key in relation R2. In that case, the value should not be equal to null. So if you get null value, it means there is no common attribute between R1 and R2. This is one more condition that has to be satisfied. Next one, same topic little extended into point 3. So the common attribute must be a key. So just now I explained that one. So when you put an intersection operator between R1 and R2, I said the value should be not null. Of course, this is not null, fine, but what value should be in place of not null? So it can be any of the attributes of R1 or R2, because this attribute of R1 is acting like a key in one relation, or it's also acting like a key in the other relation, or I can say foreign key in the other relation. So this has to be any of these values. When you have these three conditions that are satisfied, then you can say a particular decomposition has promised a lossless condition. Next one is dependency preservation. So what is this dependency preservation? Let me say it again, or let me repeat. Dependency preservation is nothing but if you are decomposing your R. So looking for the so if you are decomposing your R relation into R1 and R2, R relation into R1 and R2, each of these relation has its own functional dependencies, set of functional dependencies. So these functional dependencies should be preserved for the next level also. And if you rejoin this R1 and R2, same functional dependencies should come back. Of same original functional dependency should be reflected. You see. So when you apply a union operator between functional dependencies of relation R1, R2 and so on up to Rm, that means this union operator should give me back the original set of functional dependency. So if the decomposition is not dependency preserving, some of the dependencies is lost in the decomposition, which is not okay in the process of decomposition. So if you are having any loss in the dependencies, then that decomposition is not at all acceptable. Let's move further. That is the concept of normalization. Let's see what is this normalization going to do. So normalization is something which is going to play a key role in organizing the data. Key role in organizing the data. So right now you have studied the concept of redundancy reduction and also the concept of decomposition along with lossless and preserving lossless preservation. So along with that one, normalization is also something which is going to play a key role in organizing the data according to the categories. So here you have a set of rules that you have to follow in organizing the data. So before that, let's be little clear with the concept of normalization. So look into each of the sentences over here. So what is it saying? Normalization is used to minimize the redundancy from a relation or set of relations. So this is again something which is going to help you in reducing the duplication of data. And this is also used to eliminate the undesirable conditions in the process of insertion, updation, deletion anomalies. So what is this exactly going to do? It is going to divide, the normalization process is going to divide the larger table into smaller table and links them using a relationship. So you're not just splitting like how you have done in decomposition. So once you divide the large table into small tables, you are also creating a relationship in ready with this table so that you can retrieve the data whenever you want in a very easier manner. So now we will be looking into different types of normalizations. So each type of normalization what you're going to study right now will carry a set of rules. So what are those rules? Let's see further. The first one is the first normal form. So this normal form says, or it has only one condition in it. What is the condition? As per the rule of first normal form, an attribute of a table cannot hold multiple values. An attribute of a table cannot hold multiple values. Then what should it hold? It should hold only the atomic values. It should hold only the atomic values. So what does it mean? Look into the example directly. So I have a table called as a company or a which carries attribute called as roll number, name and the course. If you look here, what is that I'm going to do? I have just done, what is that I did? I've entered two courses in a single domain. Two courses in a single domain, C, C++ in a single domain, C bar DBMS in a single domain. That means this person whose roll number is 1 is undertaking two courses, C and C++, which has been entered in a single table itself, single domain itself, which is not at all encouraged in the database management system. So if you try to start entering multiple values in a single domain in your own way, so here they have put bar, some other person would use a comma and start entering multiple values in that. So in that case, when you write your query, so pull out the data of a roll, data of those students who are taking course C. So can you find only C over here, any of this domain, because C has been linked up with other courses? In that case, the compiler would be in a confusion. Where is this value? Where is this domain carrying C is being displayed? So this, don't you think this is leading to inconsistency condition? Yes, exactly. So that's why the first normal form in the normalization concept says a domain should carry only atomic values. It should carry only atomic values. So how to overcome this condition? So you can proceed something in this way. So roll number repeated 2 times and you can write your course separately. And next one again, roll number 3 is repeated 2 times and the data of name is also repeated 2 times, and then you can write the course. So now do you think the solution 1 is okay? Not at all, because it is leading to redundant data in the same table. So I'm not okay with this condition. Let's proceed further. Next one is solution 2. So what is the solution going to do? So roll number name is kept as it is. Now I have started splitting the course data as course 1 and course 2. So if you look here or if you observe, even the course data is encouraging redundancy. So again, I'm not okay with this kind of condition. So instead of that, you look into the third solution, which is proved to be the best. So the main table, that is last table, has been split into two tables, that is table 1 and table 2. And first table is carrying out the details of the student, and that is the name of the student along with the roll number. And the second table is carrying out the data of the course. So in this case, you can retrieve the data whenever you want from both the tables. So next one is the second normal form condition. So let's look into the conditions or rules of second normal form. So the first rule of second normal form is table should be in the first normal form. The first rule is before proceeding to the second normal form, the first normal form condition should be satisfied. So if in case the first normal form condition is satisfied, so what is the first normal form condition says? There should not be any atomic values. That means multiple entries should not be increased. If that condition is satisfied, now you can proceed and check for second normal form. So what is the second normal form says? No non-prime attribute is dependent on the proper subset of any candidate key table. So let's know what is a non-prime attribute first. So non-prime attribute is something which is not a key. I'm making concept very simple. Non-prime attribute something which is not a key. It's not at all a key. So if you filter out all the non-key elements, those are called as non-prime attributes. So these non-prime attributes, if they are dependent on any of the proper subset of a candidate key, this should not be allowed. It should not depend on any of the subset of candidate key or the candidate key. Let's try to understand this one with an example. Assume you have the data of a school which is carrying teacher ID, subject and teacher age. So what is the candidate key of this one? That is teacher ID. Teacher ID. Now you look here, what is a non-prime attribute you have? Non-prime attribute means which is not a key. So it can be the subject, and it can also be the teacher age. Now you see you see and check whether this particular thing is depending on the candidate key or not. That is the non-prime attribute, that is teacher age is depending on teacher ID or not. Let's check. Obviously, when this teacher age or the teacher data is dependent on teacher ID, which is a candidate key. But what is my second normal form saying? It should not depend on the candidate key. But in this case, it is depending. So what should be done? This particular table, what we have spoke here, is violating second normal form condition. So how to overcome this one? To overcome this, what you have to do is you just create or just split the major table into two different tables, teacher ID and teacher age. And in that, you just segregate the teacher ID with the teacher age, and you keep one more table, that is teacher ID with the subject. Teacher ID with the subject. Now, if you look here, teacher ID is a separate one, that is you need not segregate the candidate keys, because here you have only one key over here and you don't have any combination of keys, so that you can check for the dependency. Yes, we are splitted and both the tables are acting independently, so you need not check for second normal form. It's already satisfied. So let's proceed for the third normal form condition. So third normal form condition says, before proceeding for a table to check whether it is in third normal form or not, before that it has to be in the second normal form. The first rule is the table must be in the second normal form first. Next, you can go for checking the third normal form. If you feel that if you found the table that you are working on has already satisfied second normal form, now you can check for the third normal form. So what is this third normal form saying? Transitive functional dependency of non-prime attribute on any super key should be removed. So transitive functional dependency means, just now you studied there, right? A tends to B, B tends to C. In that case, A tends to B, B tends to C, and in that case, A tends to C. So that means it is creating an indirect relationship between A and C. So this kind of indirect functional dependency should be overcome. Let's proceed with an example. So you have a table called as company, where the complete set of attributes related to the company has been dumped in a single table, where employee ID, employee name, employee zip, employee state, employee city, employee district has been arranged in a single table. So if you look here, employee zip is something which is going to carry the data of the employees, data of the city and the district, isn't it? So what is happening over here? So try to form the super keys over here first. So what are the super keys? Super keys is nothing but the combination of different keys. So what are the keys you have here? Employee ID. So this employee ID in combination of employee name is also a super key. Employee ID in combination with any other attribute is also forming a super key. And what are the candidate keys you have? Employee ID is a candidate key. So apart from this candidate key, so if you remove employee ID, which is a candidate key, remaining all the attributes are called as non-prime attributes, isn't it? Like how I said. So what are non-prime attributes? These are something which are not a part of candidate key. So of course, I have removed the candidate keys. That means all the remaining attributes are non-prime attributes, isn't it? Now let's check for the dependency of these non-prime attributes on the super key. So if you observe here, this employee zip, I'm naming it as B. So I'm renaming this one. Employee zip is named as B and employee ID is named as A. And this complete combination of employee state, employee city and district are named as C. So if you look for the dependency, A is depending on B. B is depending on A. At the same time, C is depending on B. Now, don't you think this employee ID is also determining employee state, employee city or employee district? Or let me say this way. This employee state, employee city, and employee district are not only depending on B, they are also depending on A in an indirect manner. You agree with me? Using a transitive property, because I'm repeating, A is determining B and B is determining C. Don't, in that case, A is also determining C because it is following a transitive property. So this should not happen in third normal form condition. This should not happen in the third normal form condition. So what should be the solution for this one? Again, decomposing or splitting your main table into multiple tables. So the employee ID along with employee name and employee zip has been kept in one table, and the employee zip data which carries the data of employee state, city and district has been held in one more table. So this is going to satisfy the third normal form condition. If you want, you can check it. So last one is Bcnf, that is Boy's Code normal form condition. So I can say this Boy's Code normal form condition is an advanced version of third normal form. So I was saying like there should not be any transitive functional dependencies between the set of attributes in the non-prime or the non-prime attributes. Then what should be the solution in writing the functional dependency? That solution has been clearly mentioned in Boy's Code normal form. So it simply says the left hand side part should be a key super key. So if you try to plan your functional dependencies in such a way that the left hand part is a super key always, in that case super key always, in that case the third normal form is always satisfied. The Boy's Code normal form is always satisfied. That means the X what I have written should always be a super key. So let's go to the example. Assume there's a company where employees work in more than one department. So how many departments the employees are working? They're working in more than one department. In that case, the employee ID will be repeated again and again. So among this employee ID, employee country and employee department, department type and department number, which one is a key for me? So I have created a super key, that is employee ID and employee department. So if you are trying to write your if you are trying to check for the Boy's Code normal form condition for this table, this employee ID is determining employee country and employee department is also determining employee type, employee department number. So is this employee department a key over here? No. So in that case, the Boy's Code normal form condition has been violated over here. So what is it saying? The table is not in Boy's Code normal form because neither of the employee department nor employee ID are alone keys. Because this employee ID what I am speaking here, the employee ID what I spoke here is being repeated again and again. If the key value is something we should not repeat, the values are being repeated. So employee ID cannot be taken as key. At the same time, employee department cannot be taken as key. In that case, Boy's Code normal form has been violated in both the cases. So to overcome this, you just decompose the above table into three different tables. The first table is employee ID with employee country, and next one employee department and employee department mapping. So you're linking up both the employee department and employee ID. So that means a separate table linking up both the key attributes. So now you see employee ID can be taken as a separate key. So as this is a key, obviously Bcnf is satisfied. And next case, department, employee department, this is one more key, and here also Bcnf is satisfied. So this is about the different normal forms of normalization forms, that is first NF2, NF3, NF and then Bcnf. So all these rules are to be taken care while splitting your tables into small tables. So splitting cannot happen as we like. There are few set of things that has to be kept in mind which were discussed just now. Hope the concept is clear. So let's meet again in the next session, that is in the transaction management system. So thank you everyone.